Okay, so let's imagine an infinitely large plane with uniform surface charge density. So there's positive charge on this plane. And, well, we know from Gauss's law that we can get the electric field in a straightforward way. But what matters is that, of course, electric fields diverge radially away from charged particles, but given the distribution of charge, by symmetry, we know the electric field has to point directly away, can't have any sideways components. So above the plane, it looks like that. Below the plane, it looks like that. And by Gauss's law, we know that the distance from the plane doesn't matter, and therefore the electric field cannot change in magnitude, and so it has to be some constant times the normal vector, the unit normal vector, meaning pointing away from the plane. So I don't know, if this is the, say, z direction, then we can say that the electric field is equal to ck hat for z greater than 0, and E is equal to minus ck hat for z less than 0. And let's consider the curl and the divergence. So the curl of the electric field, right, we have partial derivatives of the electric field components, but the electric field components are all constant, so this is 0. We also can see from the geometry that there's no curl, given our sort of intuition about what a curl is. Is there a divergence? Well, the electric field is diverging away from charge, so in some sense it's diverging away from this plane, yet when we consider the divergence, we again think of partial derivatives of the electric field components, and so that looks like, given that they're all constants, that's 0. And we're running into the same issue we had before for a point particle, right? The electric field of a point particle, it looked like the divergence was 0, but all the action happened at the particle. The same is true here. All the action is happening at the location of the charge, which is at this plane. So as we cross this plane, that's where all the action happens. So let's look more carefully at the partial derivative of the z component with respect to z, right? That's the only component in the divergence of the electric field that we need to consider. And this is basically the limit well, let's say epsilon goes to 0 of the electric field as we're crossing this region. So z is going to difference in z, right? There's a difference in z. So let's write this as electric field above, which is, so this is c. At z above 0, it's c, and z below 0, it's minus c, right, the component. And so we have c minus a minus c divided by the difference in z, which is epsilon. And that epsilon is going to 0, and so this is going to infinity. Right, so in other words, divergence of the electric field is not 0 everywhere. It's actually, so the divergence of the electric field at z equals 0 is equal to infinity. So we see the same thing that we saw for the point particle. All the action is happening at the location of the charge, and therefore the density of charge is not everywhere 0. It's a delta function.